In Part 4 of Microprocessor Facts, we will focus our attention on the subject of memory. As the processor responds to instructions and commands provided by the operating system and application software, we need a place to store all the zeros and ones. The processor includes a cache memory on the chip that can store data temporarily. This is a memory structure that can read and write data very fast to speed up operations. At the systems level, we have memory modules that plug into the main printed circuit board. This provides a large random access memory structure that is used by the operating system and applications. The cache memory on the processor chip is usually static random access memory, or SRAM, and the larger system memory is dynamic RAM, or DRAM. The data stored in these memories is only valid if power is applied, so when you boot a computer, the operating system must be loaded into DRAM before any applications are able to function. DRAM is composed of billions of tiny capacitors that store an electric charge. A charged capacitor is a binary 1, and a capacitor without a charge is a binary 0. These memories are very dense, which makes it possible to pack the most bits on the silicon chip. The charge on each capacitor decays over time, so it is necessary to refresh the memory to maintain the data. We will build a single-bit memory cell to demonstrate how the DRAM functions. This circuit includes 4 switches to simulate the write, refresh, and read operations, and an LED to indicate that the output from the read amplifier is 0 or 1. We can also monitor the charge on the capacitor by connecting a meter to the test point. When power is applied to the memory cell, we can assume that the capacitor is in a discharged state, so if we initiate a read operation, the result should be a binary 0. Now, let's assume that some data needs to be stored in the memory. A write operation is performed by the memory controller, and a binary 1 is written to the cell by applying a pulse of voltage to the capacitor. We can see that the meter indicates a charge is now present on the capacitor. This charge can be maintained for a finite period of time. Eventually it will decay to a level that can no longer be read as a binary 1. When the read amplifier connects to the capacitor, some of the charge is used to turn on the transistor, which in turn lights up the LED. The memory controller can then apply a refresh cycle to restore all of the binary 1 capacitors to a fully charged condition. If we need to write a binary 0 to a cell that is in a binary 1 state, the memory controller will turn on the write 0 transistor, which pulls the capacitor to ground, thereby discharging it. If we now read the state of the memory cell, it will not turn on the read transistor, so the LED will be off, indicating a binary 0.